Hello everyone, this is Adnan and welcome to Chemistry with Adnan. On this YouTube channel, we are covering the entire IGCSE Cambridge Chemistry syllabus. The course code is 0620, and I am also covering the syllabus of other exam boards such as AQA, EdXL, OCR, and each has its own dedicated playlist. So if you are registered with another exam board which is different from Cambridge, so you can check your relevant playlist. All right, so in this lesson we are covering 3.3, the mole and the Avogadro constant. This is considered to be one of the most challenging topics for students of GCSEs and IGCSEs, because it involves lots of calculations, and many students, they struggle with these calculations of moles and stuff. So this is going to be an extensive lesson, and I'll be covering all the topics. So this is basically, it is focused on supplement the extended syllabus. So this topic 3.3, it has only one subtopic for the core students, which states that, like, state that concentration can be measured in grams per dm cube or mole per dm cube. But the rest of the subtopics, such as that the mole, calculations related to mole and Avogadro's constant, relationship among substances, and molar mass and like molar gas volume, and stoichiometric relationship, limiting reactants and stuff, and using the experimental data from a titration to calculate the moles of solute, or the concentration or volume of a solution, and then calculating empirical formula, calculating percentage yield and stuff. So this is going to be an extensive lesson. I'll be addressing all these subtopics one by one, and then at the end of the lesson we will be practicing some questions from the past papers as well. So the first one is, this is for core students: state that concentration can be measured so in grams per dm cube or mole per dm cube. So what is concentration? So for example, if you have a glass of water, and the volume is, let's say, 250 milliliters, right? And let's say you add 2 moles of sodium chloride in this beaker. So what will be the concentration of this solution, right? So we have 250 milliliters of water, which is our solvent, and we have 2 moles of sodium chloride, which is our solute. So solute and solvent, they are combining together to create a solution. So now the concentration can be reported in 2 units. It can be reported in moles per dm cube. So we can say that the concentration is 2 moles divided by 250 milliliters. So we have to convert it into a dm cube. So 250, in order to convert from milliliters to dm cube, we divide it over 1,000. So that's gonna give us 0.25, right? So uh, 2 divided by 0.25, and this is going to be 8. So and the unit will be 8 moles per dm cube, right? So this is going to be the concentration of this entire solution. So now we can also express it in grams per dm cube. So what will be the concentration in grams? So if we have 2 moles, right, so what will be the like molar mass of sodium chloride is, like, sodium is 23 and chlorine is 35.5, so it is 58. So 58.5 times 2. So we convert it into grams, right? So 58.5 times 2, we get 117 grams, right? So now we by dissolving 2 moles, we mean that we are basically adding 117 grams of sodium chloride, because 2 moles of sodium chloride is equals to 117 grams of sodium chloride, right? So 117 divided by 0.25, so this is going to be 117 divided by 0.25, and this is gonna give us 468 and grams per dm cube. So this is how we calculate concentration in grams per dm cube or moles per dm cube, right? So these are the two formulas. So moles over the volume in dm cube, and this will give us the concentration in moles per dm cube. So moles per dm cube will be the unit, and mass in grams divided by volume in dm cube. So this will give us concentration in grams per dm cube, right? So this is how we calculate these. So this is the only topic, 3.3 core for core students. Now the rest of the lesson is for students registered for extended. So supplement two topic subtopic 2 state that the mole is the unit of contains 6.02 times 10 to the 23. This is 6.02 times 10 to the 23rd power particles, atoms, ions, molecules, and this number is the Avogadro's constant. So this is relatively simple. What we need to understand here is that mole is a unit, just like a dozen. So if you know what dozen is, so dozen is a unit which is used for 12 things, right? And so 1 mole is equals to 6.02 times 10 to the 23 things, right? And these things can be atoms, and they can be ions, and they can be molecules, depending on what we have, right? So for example, if we have 1 mole of sodium, so we will say that it has 6.02 times 10 to the 23 atoms, right? So it's an element. So elements are made up of atoms. And if I say that I have 1 mole of hydrogen gas, H2, so then it will contain 6.02 times 10 to the 23 molecules, because we have a molecule, right? It is not in its elemental state, it is not in its atomic state. Similarly, 1 mole of carbon dioxide, it will also have 6.02 times 10 to the 23 molecules, because it is a molecule, right? It is made up of different atoms combined together. It's a molecule of a compound. Okay, so and for like ions, right? So let's say if we have 1 mole of Cl minus, so it will have 6.02 times 10 to the 23 ions, because it's an ion, right? We are dealing with ion here. It has a negative charge. It's an anion. And another example, so when we have ionic compound, so let's say if 1 mole of sodium chloride, which is ionic in nature, so we use a different word. So it will contain 6.02 times 10 to the 23 formula units, right? Formula units. So this is how we relate moles with this Avogadro's number, right? So now we move on to the next one, which is use the relationship of mole mass. Okay, so now let me explain. Mole, it has a relationship with particles, as we just saw, that 1 mole can be equals to Avogadro's number of particles. So by particles I mean 6.02 times 10 to the 23, and it also has a relationship with molar mass, right? Molar mass. So When the atomic mass is taken in grams, so that will become that becomes equals to 1 mole. So let me explain. Let me give you a few examples. And okay, so let's say we have 1 mole of hydrogen, right? So 1 mole of hydrogen, it will have 6.02 times 10 to the 23 atoms, because it is in its atomic state, right? And its molar mass will be 1 grams from the periodic table. Its atomic mass is 1, so we will write it as 1 gram. So now, since all three of these values are equal, so I can say that 1 gram of hydrogen contains 6.02 times 10 to the 23 atoms, and you know 2 grams of hydrogen will contain 2 times 6.02 times 10 to the 23 atoms. So this is important that you should practice this. So converting number of atoms into moles and mass, and converting mass into moles and number of particles. So let me give you some a few more examples. So let's say we have 23. Let's say we have 6 grams, for example. We have 6 grams of sodium, and how many moles? How many moles will there be? So we know that in 23 grams of sodium, which is the molar mass of sodium, we have 1 mole. 1 mole is equals to the molar mass you see here, this relationship. So in this way, you will not have to memorize any formula. So you just understand this relationship, and you will be able to calculate the unknown value. But I will introduce a formula as well. So 23 grams of sodium is 1 mole. So 6 grams of sodium will be equals to X. So now we just have to cross multiply, right? So 6 times 1 divided by 23. So 23 divided by 6 divided by 23, we get 0.26. So 6 grams of sodium will be equal to 0.26 moles, right? Okay, so now let's say we have 2.71 times 10 to the 22, or 22 atoms of sodium, for example, right? So what will be the number of moles, and what will be the mass? So we understand that in 1 mole of sodium, we have 6.02 times 10 to the 23 atoms, right? So if we have 2.71 times 10 to the 22 atoms, so how many moles will there be, right? So you can simply uh, you know set up this relationship where you can cross multiply to find the value of X. So this is going to be 2.7 at given atoms. So the given atoms are 2.7 times 10 71 times 10 to the 22 divided by the Avogadro's number. So 6.02 times 10 to the 23, and this will get you the number of moles of sodium, right? So you should be able to use the calculator effectively to solve this expression to get the right answer. Okay, so formulas to this. So if you have to find moles and masses given. So the formula is moles equals to given mass divided by the molar mass, right? And if moles are given and you have to find mass, so the formula is mass equals to number of moles times molar mass. And if we have a number of atoms, and they're asked to you're asked to find moles. So given number of atoms divided by the Avogadro's constant, Avogadro's constant, and this is going to give you the moles. And then once you get moles, so you can change it into mass by multiplying it with the molar mass, right? So these are some of the formulas that you can use, and we will practice it further in uh, you know uh, when we solve questions from the past papers. So now topic number 4, use the molar gas volume. Okay, so just like mole has a relationship with number of particles, it and molar mass or mass in grams, it also has a relationship with volume, which is called molar volume. But we have two conditions here. The first one is if the gas is stored at standard temperature and pressure, where temperature is taken as 0 degrees Celsius and pressure is 1 atmospheres. So this condition is called standard temperature and pressure. This is temperature, this is pressure. So if 1 mole of a gas is kept at standard temperature and pressure, so 1 mole of any gas, 1 mole of any gas kept at standard temperature and pressure, it will occupy a volume of 22.4 dm cube. So remember that 1 dm cube, it is the same as 1 liters, right? So this is at STP, and we have another standard which is called RTP, room temperature and pressure, where room, instead of 0 degrees Celsius, room temperature is considered, and the pressure is the same, right? So 1 mole of any gas, if it is uh, kept at room temperature and pressure, so it will occupy 24 dm cube, or 24 liters of volume, right? So you can see that, since temperature is increasing from 0 to room temperature, so volume is also increasing. So we have a direct proportionality, linear relationship between temperature and volume. Remember that. So okay, so now we will be practicing questions based on this in our, like, at the end of the lesson. But at this point, this is what you need to know. Now, calculate stoichiometric reacting masses, the limiting reactants, volume of gases. Yeah, okay, now we can apply what we have studied in the subtopics above, topic 2, 3, and 4, here. So in calculate stoichiometric reacting masses, limiting reactants, volumes of gases at RTP, volumes of solutions, and concentrations of solutions expressed in grams per dm cubed and moles per dm cubed, including conversion between cm cube and dm cube. Yeah, we have already talked about this. If a value is in a centimeters cube and you have to convert it into a dm cube, you divide it by 1,000. And if value is in a dm cube and you have to convert it into a cm cube or milliliters, right? So remember, 1 milliliters, it is the same as 1 centimeter cubed. So this is going to be yeah. So here you have to multiply this value by the value in milliliters or centimeters cubed to convert it back into a like to convert from dm cube into a cm cube. So this is how you carry out these conversions between cm cube or milliliters into dm cube, and from dm cube back to centimeters cubed or milliliters. All right, so now I'm going to write this equation where the sodium is reacting with chlorine. So it is producing sodium chloride. So this is to balance this equation, I put 2 here and I put 2 here. Now the equation is balanced. And yeah, now what okay, let me give you a question. Let's say we have 0 0.6 moles of sodium reacting with excess excess chlorine. Chlorine is in excess. So what will be the amount of sodium produced, right? So we can see the standard relationship between from the equation that it is 1:1, right? So 2 moles of sodium, they are producing 2 moles of sodium chloride. So now whatever the moles of sodium are, the same will be the amount of sodium chloride produced, right? When you cross multiply 0.6 times 2 divided by 2, you get 0.6. So this will be the answer, that if we use 0.6 moles of sodium, we will get 0.6 moles of sodium chloride, because the mole ratio is the same, right? So similarly, this question can be converted into grams as well, right? So let's say that if the question says that uh, you know 11 grams of sodium is reacting, right? So what will be the mass of NaCl produced? So now you can see that in the balanced chemical equation, 2 moles of sodium are reacting. So you have to convert this into grams, right? Or you can convert this into grams as well. So in both ways you will get the same answer. So you can convert this into moles, 11 grams into moles, and then finally when you get the moles of sodium chloride, then you can convert it into grams. So okay, let's do this. Instead of changing these moles from the balanced equation in grams, we can convert this equation, this value from mass to moles. So 11 grams divided by 23, we will get the moles of sodium, right? So 11 divided by 23, we get 0.47 moles, right? So now from the balanced equation, we can see that the mole ratio is 2:2. So 0.47 grams moles of sodium, they will produce 0.47 moles of sodium chloride. So now we can convert these moles into grams. So the formula is mass equals to moles times the molar mass, right? Relative molar mass. So relative molar mass of sodium chloride is 58.5. So this is going to be 0.47 times 50 times 58.5, 58.5. So this is going to be 27.4 grams. So this is how we interconvert these values, right? So let's say now if in a chemical equation a gas is involved, for example, N2 is reacting with 3H2 producing 2 moles of ammonia. This is the balanced equation. So let's say we have you know 0.36 moles of nitrogen. They are reacting with excess hydrogen. Why am I saying excess again and again? Here I have used excess, the word excess, and here I've also used the word excess. I will explain it when we will talk about limiting reactants in our next topic. Like within this lesson, I'm going to explain it in a few minutes. So for now, 0.36 moles are reacting with excess hydrogen to produce ammonia. So yeah, now what will be the volume of ammonia produced? What will be the volume? And the reaction, this reaction is taking place at STP. So you must look for whether the reaction is taking place at STP or RTP. So sometimes they give you STP, sometimes they give you RTP. So you have to calculate accordingly, right? So these values must be taken accordingly. If it is occurring at STP, so you will use this value in your calculation. If the reaction is taking place at RTP, you will use this value in your calculation. So now, since our reaction is taking place at standard temperature and pressure, so step one, so you see it's 1:2. One from the balanced equation, we can see that the mole ratio is 1:2. So if 0.36 moles of nitrogen are reacting, so 0.36 multiplied by 2, right? So 0.36 times 2, and 0.72 moles of ammonia will be produced. So now we know that 1 mole of any gas occupies 22.4 dm cube at standard temperature and pressure. So 0.72 moles, they will occupy how much volume? So you just multiply this. So 0.72 times 22.4, and that's going to give us 16.12 dm cube. This is the volume, right? So this is how we calculate volumes of gases at RTP. Yes, so this is RTP. I gave you example of our STP. Let's say if this reaction is taking place at RTP, so the only difference is that you will multiply this, you will change this value here, and this value will become 24. So 0.72 times 24, and that's gonna give us 17.28. This will be the volume dm cube at RTP, right? So I solved for both the values STP and RTP. Okay, I hope this is clear. And now volumes of solutions and concentrations of solutions expressed in grams per dm cube and moles per dm cube. Okay, so now uh, for solutions, molar calculations are a bit different, but I have already explained the formula in our first topic here, which is for core. So these are the two formulas that we use: moles over volume and grams over volume, and the volume in both of them is dm cube, right? So now let me give you a few questions here, and the question will be, but I think instead of going to let us calculate let us try to understand limiting reactant first, and then we come back to volumes of solutions and concentrations. Okay, so volume. What is a limiting reactant? Okay, this is interesting. This is considered a difficult topic. Many students struggle with this, so I want you to pay attention here. So limiting reactant, you see, in a balanced chemical equation, the reactants, they react completely with each other, right? And when the reaction goes to completion, all of these reactants, they change into products. Like they react completely. When this reaction goes to completion, we will not have anything here remaining, right? And all of this mass or moles, they will be converted into ammonia. But when they are reacting in a balanced chemical equation, so for example, you can see here that 1 mole of nitrogen is reacting with 3 moles of hydrogen, right? Hydrogen gas. So this is the mole ratio. So as long as you respect this ratio, both these reactants, they will react completely. And for example, 2:6, right? And then you can uh, take any ratio, but it must match this 1:3, because 1:3 is the simplest standard ratio. So even if you react at 2:6, they will react completely. So now what happens when we do not respect this ratio? We try to react reactants other than the ratios given in the balanced chemical equation. So when that happens, one of the reactant becomes a limiting reactant, meaning that it will get consumed first, and the other one will become a reactant in excess. So let me show you. So let's say let me represent moles with boxes. So from the balanced chemical equation, 1 mole of nitrogen is reacting with 3 moles of hydrogen, right? And producing 2 moles of ammonia. So 1:3:2. So now the standard ratio is 1:3. Now let me disturb this ratio. Let's say I insist that I'm going to react 2 moles of nitrogen gas with 3 moles of hydrogen gas. What will happen? So will the amount of ammonia, the moles of ammonia, will they increase? Will they decrease? Will they remain the same? Yes, they will remain the same. Why? Because when 1 mole of nitrogen will react with 3 moles of hydrogen gas, this is the ratio from the standard equation, from the balanced equation. So 1 mole of this hydrogen will be used up, all of it, and this 1 mole of nitrogen will also be used up. So they will create 2 moles of ammonia, and at the end of the reaction, there will be 1 mole of nitrogen left unreacted. So what is a limiting reactant? Limiting reactant is something that gets used up first, and the excess reactant is the one that is left behind, in a chemical reaction, that is left unreacted, right? So excess reactant will be left unreacted, and yeah, I hope this is clear now. So in a question, if let's say, now let me give you a question. So N2 plus 3H2, and this is producing ammonia, NH3. So if they change the mass or moles of both these reactants, so you must have to find the limiting reactant first in order to calculate the amount of ammonia. For example, so 0.23 moles of nitrogen is reacting. Now I'm not writing excess here. Instead I'm writing, let's say, one mole, right? So now I changed the moles for both the reactants, and this is not following the standard ratio. So the question is 0.23 moles of nitrogen, they are reacting with 1 mole of hydrogen gas. What will be the amount of ammonia produced? So now you cannot relate the mole ratio between nitrogen and ammonia, or hydrogen and ammonia, to find the amount of ammonia before solving for the limiting reactant, because limiting reactant will react completely and it will give you the correct yield of ammonia, right? If you choose excess reactant without confirming which one is a limiting reactant, so it will give you an artificially higher yield, because it will not react completely, right? So the yield that will be collected by comparing the mole ratio of an excess reactant will be artificially higher, and the answer will be incorrect. Okay, so now let me solve it, and explain it to you, that what exactly I mean. So in order to find a limiting reactant, step 1, you write the standard ratio from the balanced equation. So nitrogen is 1 mole, and hydrogen is 3 moles. And now we cross check. So let's say if we are using 0.23 moles, so how much actually hydrogen is required? We have 1 mole, but we are cross checking this step is called cross checking. This is step 2, right? So step 2, we cross check this amount. So so 0.23 multiplied by 3 divided by 1. When we cross multiply, so 0.23 times 3, we get 0.69 so moles. So you see, we have 1 mole, and we have more than what is actually required, right? So 1 mole of hydrogen is more than 0.69 moles, which is actually required. So this reactant hydrogen will be our excess reactant in this case. So hydrogen is in excess, right? So if it were less than what was actually required, like if it were less than 0.69, let's say 0.5 or 0.4 or zero point 0.3, so then this would have been an excess, a limiting reactant. Hydrogen would have been a limiting reactant, but since it is higher, so hydrogen is a limiting is an excess reactant, and nitrogen in this case is our limiting reactant. Limiting reactant, right? And now we have to find the moles of ammonia. So we will use the standard ratio of nitrogen and ammonia, right? So we will not consider hydrogen because it is not reacting completely. Okay, so what do I mean by it is not reacting completely? So 1 minus 0.6 0.69. So 0.31 mole of you know uh, hydrogen will be left unreacted, right? So it will not react completely. 1 mole will not react completely. So this is why the amount of ammonia that we will calculate using 1 mole will be incorrect. So now 1 mole of nitrogen from the balanced chemical equation, it is producing 2 moles of ammonia. So 0.23 moles of nitrogen. So now we have to double this because the mole ratio is 1:2. So this will be 0.46 moles of ammonia, right? So this was about limiting reactant. And yeah, now use the experimental data from a titration to calculate the moles of solute or the concentration or the volume of a solution. Yeah, so I'm combining this topic with this one where it says that volumes and solutions and concentrations of solutions. So now let me just write a question for you, and then I'll explain that accordingly. So let's say 20 milliliters of 0.1 mole per dm cube HCl reacts with 25 milliliters or centimeters cube, because these are the same units, of NaOH, sodium hydroxide. 20 milliliters of 0.1 mole per dm cube HCl reacts with 25 milliliters of sodium hydroxide. Find the concentration of sodium hydroxide. Okay, so how do you solve this question? Step one. So mostly balanced equation is given. If not, you write it for yourself. So HCl, it's a neutralization reaction. When HCl reacts with sodium hydroxide, it creates salt and water. So double displacement reaction or neutralization reaction. NaCl plus H2O, and the equation is balanced. Yeah, hydrogen, two hydrogens, one chlorine on each side and one sodium on each side. Yeah, so the mole ratio is 1:1:1:1. Okay, now you see the formula that we will be using is concentration equals to moles over volume, right? So in the first step, uh, for HCl, you can see that both concentration and volume, they are both are given, right? So we can calculate the number of moles of a substance by using this formula if concentration and volume both are given, right? So we rearrange this equation. This will be moles equals to concentration times volume. And remember, this is a very, very important point that pointing out, and I'm putting emphasis on this, that the volume must be in a dm cube. So you must convert these volumes. So 20 divided by 1,000, in order to convert from milliliters or centimeters cubed to a dm cube, you divide by 1,000. So this will be 0.02, and concentration is 0.1. So 0.1 times 0.02 will get you the moles of HCl, right? So 0.1 times 0.02, and 0.1 times 0.02, you get 2 times 10 to the negative 3, right, moles and of HCl. Okay, so this is step one, right? So what is step one? Find the moles of the reactant whose concentration and volume both are given. You cannot find the moles of sodium hydroxide because its concentration is not given, it's only volume is given, right? So you have to find concentration. So step one, find the moles of a reactant whose concentration and volume both are given. So now we use the mole ratio from the balanced equation to find the moles of the other reactant. So it's 1:1. So if the moles of HCl are 2 times 10 to the negative 3, so the moles of sodium hydroxide, they will also be 2 times 10 to the negative 3. Now that we have moles of sodium hydroxide, so now step 3, it is very simple to calculate the concentration. So formula, we already know that it is moles over volume. So volume for sodium hydroxide is, it is given, it is 25 milliliters. So don't forget to convert it into dm cube. So this is 0.025, and moles are 2 times 10 to the negative 3, right? So 2 times 10 to the negative 3 divided by 0.025, and this is gonna give us 0.08, and this is the concentration, and unit will be a mole per dm cubed, right? So in these 3 simple steps, you can calculate concentration. Now, you can imagine, that if any two values in this equation are given, you can find the third one by rearranging the data, the equation according to the given data, right? So if if moles and concentration are given, you can calculate volume, right? And if moles and volumes are given, you can find concentration. If concentration and volume is given, you can find moles. So this is how basically the questions will appear on the final exam. Okay, so now calculate empirical formulae and molecular formulae given appropriate data. Okay, so hold on a minute. Let me just quickly create a question for this one. Usually, percentages of isotopes and are given. So let me just quickly create a question on this. Just give me a second. Okay, so I have this question. Let me paste it on the whiteboard, and let us solve it. Okay, so this question, it states that a compound contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen by mass. Its relative molecular mass is 180, and find the empirical formula and the molecular formula. So how do you find an empirical formula? We have already learned that what an empirical formula is. If you have not watched that lesson, go back and watch that lesson on empirical and molecular formula, and then come back and try to understand this. You must fill the knowledge gap. There's no shortcut, right? So how do you calculate the molecular form empirical formula? So step one, we assume that these percentages are mass in grams because they add up to 100, right? So let's say we have 40 grams in the question. We assume that carbon is 40 grams and hydrogen is 6.7 grams and oxygen is 53.3 grams. We convert these into moles. And how do we do that? In this reaction, in this lesson, in this very lesson, you learned 5 minutes ago that how to calculate moles if mass is given. So the formula is mass over molar mass. So 40 divided by molar mass of carbon is 12. So we divide 40 by 12, and when you divide 40 by 12, you get 3.33 a mole, right? And for hydrogen, since its atomic mass or molar mass is 1, so and oxygen is 16. So 6.7 divided by 1, you get 6.7 mole. And for hydrogen, for oxygen, we have 53.3 grams of oxygen. So divide that by 16 and you get 3.33. Okay, so mole. So this is step one. We assumed that the percentages are mass in grams, and we now change these masses into moles. Now pick the smallest number and divide the rest by that. So smallest number of moles is 3.33. So we divide all these by the smallest number. So for carbon, it will be 3.33. We are basically simplifying this further, right? So 3.33 divided by 3.33, and this is going to get you 1. And for hydrogen, so 6.7 divided by 3.33. So 6.7 divided by 3.33, this is going to give you 2 because it is almost equal. And now, so like it will be halved. So oxygen, it is 3.33 divided by 3.33, right? So you get 1. So here you can see that um, so this is your empirical formula. Carbon is 1, so we don't write anything. Hydrogen is 2, so we write 2. And oxygen is 1, so we don't write uh, anything, right? So when there's one atom, so we don't write that in a formula. So this is our empirical formula, which gives us the simplest ratio of atoms. Okay, now how do you convert this into a molecular formula? So in order to convert in an empirical formula, you must have the molar mass of the actual compound, right? So the molar mass must be given in the question. So this is 180, and the formula will be molar mass or molecular mass divided by the empirical formula mass, right? Empirical formula mass. And yeah, so now let us put the values. So, and times the empirical formula. This is the formula, empirical formula, right? Okay, so molecular mass is given in the question, which is 180. So 180 divided by the empirical formula. So in the empirical formula mass, carbon is 12, and we have one atom of it. So 12 plus hydrogen is 1. We have two atoms. So 1 times 2, we get 2, plus oxygen is 1. So oxygen is 16, right? So plus 16, and we get 30, right? So this is the empirical formula mass. So 180 divided by 30, 180 divided by 30, we get 6. So 6 times empirical formula, which is CH2O, which we just calculated here. And 6 times like carbon, 1 times 6, we get 6 carbon atoms. So 6 will be multiplied by 2, and this will be 12 hydrogens. And 6 times 1 oxygen, there will be 6 oxygens. So this is the molecular formula, C6H12O6. So this is how you find empirical formula, and then you convert it into a molecular formula. Remember that you cannot directly calculate the molecular formula from these percentages if MR, the relative molecular mass of the actual compound, is not given. Remember that, right? So sometimes they make it easier, they make it less lengthy. They make this question short by already giving you the empirical formula, so CH2O, and they will also give you the molar mass 180, and then they will ask you to convert it into molecular formula. So you just have to use this formula and convert it into the molecular formula, and you don't have to do all these calculations, right? So that is the short and easier form of this question. Okay, so now the last question, the last topic, it is calculate percentage yield percentage composition by mass, and percentage purity given appropriate data. Okay, so I think this lesson, it is becoming a bit too long, so I must end this lesson here. And this part where percentage yield and percentage composition by mass and percentage purity, we have to calculate. I'll explain this in another one, because lots of things are involved here, and I don't want to leave any I don't want to I don't want to miss any topic. So and the questions from the past papers, they will also be uh, solved in the upcoming lesson for 3.3. So yeah, okay, this will be all for today. I also offer one-on-one tutoring lessons. The seats are very, very limited if you're preparing for November or May, June intake. So better book early. The Google form is given in the description. And I also have a community, high school community on school.com. The link is given in the description, where I offer group lessons, and you can join my group lessons there. You can join the premium subscription. It is very cheap, very affordable, and it is a very good place to be. You can interact with other students studying chemistry all around the world, and there are some interesting questions and posts that you can participate. Right, you can share which topic is difficult for you. You can share your strategy, that how you study. So yeah, it's a good place to be if you are excited about chemistry. All right, then this will be all for today. I'll see you in the next one. Take care. Goodbye.